The side channel attack group included three primary researchers, Clay Carper, Stone Olguin, and Matthew Baer, along with 5 educators, Sandra Jocelyn, Dana Theriot, Tanya Taylor, Doc Shaw, and Jessica DeFries. Our research involved side channel attacks, finite state machines, and the analysis was conducted using simple power analysis. The title of our research project was Determining Input Values of a Finite State Machine Representing a 3-Light Traffic Signal Based on Power Consumption. Of interest to the team was whether the color and timing of a 3-light traffic signal could be determined based on power consumption. Put simply, a side channel attack breaks cryptography by exploiting information inadvertently leaked by the system, rather than targeting the code directly. For example, an attacker might monitor cache accesses made by the target in a shared environment, such as cloud services. Another attack might be based on measuring how much time various computations take to perform or on power consumption during computation. Some attacks exploit sound, while others take advantage of data that was thought to have been deleted. A finite state machine is an abstract machine that can be in exactly one of a finite number of states at any given time. That is, it is a mathematical model that will read a series of inputs. Think of it in terms of a traffic light. When the finite state machine reads an input, it will switch to a different state. In the case of a traffic light, the states are green, yellow, and red. Each state is specific and cannot overlap with another state. Other examples include vending machines, elevators, and turnstiles. Power analysis helps the researcher to determine the smallest sample size that is needed to detect the effect of a given test. In this case, power consumption is used as the side channel to determine whether the color and timing of a 3-light traffic signal could be determined after the data were collected. To begin, the Wyoming Department of Transportation presented an introduction to the hardware of a traffic light box, which showed where the information is stored and controlled. The programming is advanced and uses sensors to modify the timings when needed based on the cameras. They also explained that timings are programmed according not only to time, but also to frequency of use and location. From there, the educators collected data on various traffic signals in Laramie, Casper, and Cheyenne, Wyoming. They recorded the amount of time each signal remained green, yellow, and red. This information was passed to the primary researchers, who then utilized a chip whisperer nano device to capture and modify an underlying code base for use in the analysis. In this case, the researchers programmed the device with a simplified finite state machine. To better illustrate the underlying implementation, LEDs onboard the Nano were illuminated when emulating a traffic light, thus capturing data directly relating to the power usage of the LEDs, which constituted the contents of the collected power traces. A total of 500 traces with 30,000 power measurements were gathered for each of the 5 traffic light state machines. Data was calculated via the pointwise average for each of the 5 sets of power traces, giving 5 master traces. The images here show some of those traces, color-coded in green, yellow, and red. Blue shows when there was a pause. Each master trace represents a single timing configuration. To maintain minimal data generation, each timing was scaled down to a red to yellow to green ratio that followed X to 1 to Z. That is, each timing was divided by the provided yellow light timing. In order to accentuate the different states and also emulate the transitions, a short non-operation was performed in between each state. Additionally, each timing was ultimately scaled up by a factor of 10 to offer a stronger visual demonstration of the time spent in each of the 3 possible states. For example, if a timing was scaled down to a red to yellow to green ratio of 2 to 1 to 4, these would each be multiplied so that there would be 20, 10, and 40 peaks counted for the red light, yellow light, and green light state, respectively. Findings revealed that the color and timing of a traffic light were detectable based on power usage. For example, green lights were approximately 4 to 5 seconds, yellow lights were typically 1 second, and red lights were 2 to 3 seconds. This analysis allows for such things as the determination of which car had the right-of-way at an intersection in the event of a traffic accident. Thank you for watching. We hope you enjoyed our presentation.